All right, folks, these are the solutions to 1980, number 3. And I don't have data on the average or where the points are, the rubric for the points, because it is that old. But I think it's important to challenge yourself to think about the difference between slipping and no slipping. Okay. And then I linked to a video answers by this professor I found online, or teacher. And at the beginning of his video, he has a clip of a real billiard ball rolling without slipping. So that's a nice visual. Anyway, so check that out if you want to. Okay, so you've got a billiard ball with different dimensions. Again, they give you the rotational inertia for a sphere. So we're going to use that. Sometimes they do, sometimes they don't. But if you read this carefully, the cue stick goes through the center of mass, giving it an initial velocity v naught. The reason it had to go through the center of mass is it has an initial linear velocity because this clearly exerted a horizontal force. But because it passes through the center of mass, it's not going to make it start rotating. So omega naught is 0. So it is translating, but not rotating. So the big thing is, the big concept is, in order for something to roll without slipping, the translational speed v has a very specific relationship with the rotational speed omega. That is clearly not true because omega naught is 0 and v naught is not 0. So v naught is not equal to omega naught r. So it is slipping. But what's going to happen is, because it's slipping, we're going to have kinetic friction acting this way. So that, I don't want to confuse you, that pool stick is no longer acting. So we have the kinetic friction because the nooks and crannies were shoved across the surface instead of coming down to lock and unlock. So we have static friction, which is decreasing the translational speed, but we'll see in question B, starting to make it rotate because it causes a torque about the pivot point. Okay, so that's the big picture of what's going on. And at some point, since omega is increasing and v is decreasing, this relationship will be true. Okay, so this one's super tricky. I wish I had the average for you so that you would know. You don't have to get all the points right to do okay. But again, if you're going to get credit for testing out of this class, I think it is important for you to think about the difference between slipping and unslipping. So I do think this is still a really good exercise. Okay, develop an expression for the linear velocity v of the center of the ball as a function of time. So a couple of hints here. Velocity is tricky because it could be energy, it could be kinematics, or Sudoku, or it could be momentum. So velocity is really, really versatile, but that makes it hard to figure out. And it is traveling from point A to point B. Energy isn't conserved because we have the sliding friction, but another big fat hint is, we have time. And time could be power, work in energy and power. It could be impulse and momentum. You could do this with impulse and momentum, but that's that would be tricky. So the big fat hint, and if this were a more recent AP problem, I think they would have walked you through it a little bit more. I think they would have said draw a force diagram like the other ones. Hopefully you're doing these problems in order like the other ones we've done. So let's start with that. Let's draw a force diagram on this thing here. So it has a weight that you should draw at the center of mass. It is touching a surface. So you have the force of the normal. And again, it is skidding. Please go watch the video at the beginning of the link. So this is F, friction kinetic. It is literally skidding across the the pool table, and so the nooks and crannies are bumping along the nooks and crannies of the pool table, and there's kinetic friction. All right. So function of time means, oh, I want V as a function of time. These forces are constant. So I'm going to, and I gave you a V naught. It's going to be V equals V naught plus AT. You don't know, you know V naught. You want to keep the T in there because you want, that's your input. You want a function. The expression is another fancy word for function. So that's your input. That's a given. And that's your output. So what we need to do is find A. Oh, let's go back and look at the force diagram for A. So it's a two-dimensional problem. Vertically, the forces are balanced, so the normal equals the weight. Okay, boring problem. Horizontally, it is accelerating. That's why velocity is a function of time. But the only force you have is friction. All right, so it's not super complicated. What's hard is figuring out that it's really two different questions. It's a two-part problem, I should say. So the first thing we want to do is say, I have minus friction kinetic equals ma. Because friction is, my velocity is to the right. I'm going to call that positive. So don't confuse. So my velocity vector is positive and my friction is negative. And what's the formula for friction? Mu kinetic normal. And oh, it's a boring problem. So the normal equals the weight. And then that is super nice that the mass cancels. So my acceleration is equal to minus mu g. That's, check your work as you go. G is already in meters per second squared, and we're going to multiply by mu, which is dimensionless. So yay, that has the right units. I didn't, hopefully make a mistake, right? It's a good check. Now we're ready to go. Time is a clue that we're going to use physics Sudoku. Okay, so we want, the input is time, the output is V, so those can stay variables. Actually, everything's variables here. V naught is just some number that we're representing with a algebraic variable V naught. And it is slowing down because the nooks and crannies are taking away some of its linear kinetic energy. Okay, so that is the answer. So as people say over and over again, what is hard is not like F equals ma. You all can do that in your sleep, right? Linear velocity. What's tricky is knowing what you need to apply. And in this case, you needed to apply force diagram stuff with physics Sudoku or constant acceleration. But the individual pieces are not hard. What's hard is figuring out what do I have, what should I apply, energy, momentum, etc. Okay, that is A. I don't know how many points that was worth. Question B says, develop an expression for the angular velocity. Oops, Cami did not like that omega, as a function of time while it is rolling with slipping. All right, so hopefully if you got A, you realized, oh, B is just the same thing, except now I'm going to do torque. So we're, instead of using V equals V naught plus AT, we're going to use omega equals omega naught plus alpha T. It's nice that omega naught is 0, but I got to find alpha. So I'm going to do this down here so we have more room. So the weight isn't causing any torque because it is passing through the pivot. The normal force isn't causing any torque because it's passing through the pivot. But what is a little tricky is that kinetic friction is doing two things. It is slowing down the linear velocity, but it is also causing omega. And this is my lever arm R. What's a little tricky here is, well, let me do hands of the clock. Here is R. Here is kinetic friction. Technically, torque is rough. Technically, this is clockwise. This is negative 90 degrees. However, in this case, I find it easier to do winning minus losing. So since it is going to the right, translating to the right, I decided to call to the right positive. Since it is rotating clockwise, I am defining clockwise as positive. And then the guy in the video, part of the reason I found it, I wanted to figure out how he dealt with that or how somebody else dealt with that. So I'll say this slowly. Hopefully it'll make sense. If this wheel is rotating this way, then that's going to cause translation that way. So V equals omega R only if you define omega clockwise as positive. So for these things to be linked in an easy way, where if this rotates clockwise, it's going to translate to the right, then if you define clockwise as positive, then V equals omega R. If you want to, if you're like, I don't like that, I know clockwise is supposed to be negative, then you have a minus sign in there, and that's how he deals with it. He catches himself and says, oh, wait, V doesn't equal omega R, it equals minus omega R. Because if I want to translate to the right, which is positive, then I need to rotate to the left. And so if omega is negative, then, sorry, let me say this again slowly. If I want to rotate to the right, which I've already defined as positive, then I need to rotate clockwise. Clockwise is negative, so there's a hidden minus sign in there. So I need a minus sign in front of this in order to end up translating to the right. Okay, so hopefully that made sense. It's tricky. That is why it is easier to just say these things are arbitrary. So let's call to the right positive because it's moving to the right. Let's call clockwise positive because then V equals omega R. All the motion is positive. And I don't have hidden minus signs. Okay, so all of that is to say that even though technically this friction is causing a pure definition negative torque, we're going to define clockwise as positive so that I am going to just say RF sine of positive 90 equals I alpha. Okay, and R is easy. It's just the radius because the friction acts at the edge. F is friction, which is mu times the normal. We already proved that was mu mg up above. I'm defining this torque as positive. I is mr, 2/5 mr squared, right? I think it's a sphere times alpha. Okay, so a little bit more complicated than F equals ma. But the mass still cancels. That's awesome. One of the R's cancels. So alpha is 5/2 mu g over R. And again, I like that positive because then when we say omega equals omega naught plus alpha t, we know this is speeding up. Although, you know, speeding up isn't always positive, but anyway, this is 0. And that way the omega starts at 0 and increases linearly with time because all of these things are just numbers we don't know yet. Okay, so omega as a function of time is this relationship. So the hint again is function of time. Torque is constant, means I can combine the concept of torque causing rotational acceleration and then old school physics Sudoku. All right, then C is really, really, really tricky because time looks like, oh, now I should do physics Sudoku, but we've already dealt with the rotational and the linear physics Sudoku. But the clue is roll without slipping. Oh, what does roll without slipping mean? Oh, roll without slipping means this velocity, which is a function, equals this omega, which is a function, times t, which is just changing with time, which is time, right? So again, remember initially v started out bigger than omega because v naught was not 0 when omega was 0. So v is increasing with time. Sorry, v is decreasing with time, and omega is increasing with time until at some point this relationship is true. Okay, and we know that v is increasing with time is, and that's hopefully this is feeling, that you're better at this than you were at the beginning of the year. You feel that's a skill I think you can translate to a lot of different things, because sometimes some variables could just be a number. That's a specific speed, but sometimes that variable is a function of time, and you can just replace the entire variable with a function. That velocity is equal to this. That is how that expression is changing with time. And that is equal to omega as a function of time, which we just figured out. And at some time, this relationship is true. And that's when it changes from slipping, where these two things don't have this relationship, to not slipping. Okay, that's the trick, is what does roll without slipping mean? It means that this relationship is true, and there's some hidden functions in here, which is how you're going to solve for, the time. Okay, so everything else is algebra here. Let's add this to both sides. So you get mu g t plus, oops. Hang on. Okay, I'm like, wait, what is that R doing in there? That's not canceling. V does not equal omega t. I hope you caught that. V equals omega R. And now my R's cancel. Apologize but hopefully you caught it and you're like, yay, and that you realized you were paying good attention. Okay. But there's a T here. That's what I got confused. Okay, there's a T in the omega is a function of time. Sorry about that. This is a function of time. R is part of the V equals omega R relationship. Okay. Whew. Okay, so we have 2 over 2 mu gt plus 5 over 2 mu gt. So V naught equals 5 plus 2 is 7 halves mu gt. We care about t. So the time it takes that billiard ball, go watch that video because it's pretty cool. Just watch the first little bit of it if you want. Equals multiplied by the reciprocal. Let's see, 2/7 V naught over mu g. That is the answer. I'm going to take a little bit of time to go through a really good skill if you take more physics in college. Let's see if this makes sense. So the 2/7 comes from the relation, like the rotational inertia, like that, not very helpful. But clearly, the faster it's going, the faster it's translating to begin with, the longer it's going to take for omega to catch up to the V naught, right? Because omega started out 0, omega naught was 0. And in order for this relationship to be true, V has to decrease and omega has to increase. So clearly if V naught's bigger, that's going to take longer. But what is causing the omega to increase was the torque caused by friction. So if you imagine, this is a bird's eye view of one of those, or like a merry-go-round, bird's eye view of a merry-go-round, and you are exerting a force on it this way, that merry-go-round is going to start to rotate faster and faster and faster, right? So this is increasing, but what's making it increase is the friction. And so the bigger the friction, the bigger the coefficient, the less time it's going to take. It might be weird to think about, like, what is free fall doing in there? That gravity is not coming from free fall. It's coming from the fact that the normal force was caused by the weight. So the bigger the attraction to the Earth, the greater the normal force, the more those nooks and crannies are squishing together, and the greater my friction. Okay, so that's what that is doing in there. So these two things are really coming from friction. So as friction goes up, the time it takes to get this up to speed enough that it matches the translational speed following this relationship, the quicker that's going to happen. Okay, that is the answer to C, and that is basically all I want you to get out of this problem. I really don't like question D. I'll talk about it a little bit, but I think it's confusing. So when the ball is struck, it acquires an angular momentum about the fixed point P on the surface of the table. So here's point P, and it's translating through space. During the subsequent motion, the angular momentum about point P, so not about this new point P prime where it is point of contact later, but about point P, remains constant despite the frictional force. Explain why this is so. Calculating the angular momentum of this solid thing, it's not a blob. If it were a blob, it'd be different, and we could talk about RMV sine theta. I'm not sure I don't think it's talking about the center of mass of this thing. I don't want to go into why that's this, like R goes up, but V goes down. I think it's a bad question. I think it's confusing for the level of physics we have. But if you see something about angular momentum not changing, you know that linear momentum is conserved if there's no outside forces. Angular momentum is conserved if there's no outside torques. Okay, so I do think that's important for you to recognize and go, oh, friction is not causing a torque because it is acting at the pivot. Even if down the road, a little bit later, you still have friction, it still passes through that pivot. So the angular momentum of this system cannot change because wherever friction is, it passes through the pivot, the point that you're defining that you want to determine the angular momentum about. That seems a little hand-wavy to me because, again, this is not a blob, but that's basically what the guy said as well. So I don't love this question, and I'm gonna stop there. But I did want you to see what it means to transition from slipping to not slipping. I think it's kind of cool. There's a lot of things that if you see this for the first time, you might have said, never would have gotten that myself. And that's a fair assessment, right? Sometimes you have to see it and go, oh, okay, it's a little tricky, but now that I see it, I could do it again.